All right, in 2.7, we're going to start to take a look at some of the most common types of graphs that you guys will be seeing. So there are 4 of them. They're the constant function, the linear function, absolute value, and quadratic. And there's a bunch more that we'll be seeing throughout the year, but we're going to start with these 4. And more importantly, we're going to talk about what it means to be a parent function and what it means to transform that parent function into a different function. So first one is a constant function, and we've seen those already. So these are something of the form f of x equals a. So a is just going to be some sort of constant. So here's what the graph will look like. And each time we graph, we're going to graph the parent function. So that's our coordinate system, and the graph just looks like this. So it could be any horizontal line at all. That's what it means to be a constant function. So it's just a horizontal line. It could move anywhere up and down. The parent function, though, is just y equals 1. So when we say the parent function, that's like the original, kind of the most basic version of that type of function. So the most basic constant function is just y equals 1, so we refer to that as the parent function. So we're also going to talk domain and range for all of these. So domain is all reals. You can plug in any real number that you want, so every single x value will eventually get covered. But the range is very, very restricted. It's just a. There's just one y value that will ever get hit by this graph. So like here, the range is just 1. Only one single value gets hit. No other y values will ever get hit by this function. All right, so constant function is just a straight horizontal line. So if it was y equals 6, we would plot a horizontal line at 6. All right, so let's start to look at slightly more complicated functions. We've seen this as the identity function. More commonly, they're known as linear functions. So identity, you might see that, but usually you'll see it as a linear function. So in function notation, it's known as mx plus b. So you guys have probably seen y equals mx plus b, but this is just function notation. So here is the parent function. Parent function is just the easiest possible linear function. It goes through the origin and it has a slope of 1. So that's this line right here. Okay, so the parent function is just the line y equals x. About as simple as we can get. Okay, our domain and range, both super easy. They're both just all reals. Domain is all reals, range is all reals. And if you take a look at the graph, every single x value to the left and to the right will eventually get hit. Every single y value down and up will eventually get hit. All right, so one thing I want to point out, and these are things that we're going to be using just on the next page to actually plot these functions more specifically, is we're going to look at points. Okay, so this function right here has 3 very important points. It goes through the origin. Okay, so it has the point 0, 0. It also right here goes through 1, 1. So right here it has the point 1, 1. And then right here it has the point -1, -1. Okay, so when we start doing transformations, we're going to be doing these transformations of these 3 points. So it's really important to know what 3 points the original function had. So these are the original points that you'll use for a linear function. All right, let's look at absolute value functions as well as quadratic functions. So absolute value functions, here is the parent function for absolute value. Looks like this. Absolute value, as we learned in 2.6, is just this like V-shaped curve. Okay, so it looks like this. All right, so the parent function is just y equals the absolute value of x. It's like the simplest version of the function that we have. Domain and range, domain for every function that we've seen so far has been all reals. You're always allowed to plug in any x value that you want. And then range, for this one specifically, you only see positive values of y. See how nothing down here gets hit at all. So it's just y values that are greater than or equal to 0. The lowest possible value is 0, and then it just goes up from there. All right, so just like with the linear, we're going to talk about the original 3 points. Okay, so first point goes through the origin. So 0, 0 is a point on our original graph. We also hit 1, 1, which is right here. We hit 1, 1. And we also hit -1, 1. Because remember with absolute value, if you plug in a -1, it'll spit out a positive 1. So we also have the point -1, 1. So those are the 3 points that you would use to transform an absolute value function. And the last one that we're going to be looking at is a quadratic function. And it looks like this. So here's our parent function. About as easy as can be, it goes through the origin, and it's just that parabola-shaped curve. Looks like this. Okay, so our parent function is just y equals x squared. Okay, so that's y equals x squared. Let's talk domain and range. Again, domain, all reals. And the range is actually the same as this range. See how neither one of them go below the origin? There's no y values plotted down here. So this one has the same range. All values of y that are greater than or equal to 0. 0 is the low point, and then it just goes up from there. And finally, our 3 points. This one goes right through the origin. And then if I plug in 1, I get 1 back. 1. So if you plug in 1, 1 squared is still 1. And then it also has the point negative 1, 1. If you plug in negative 1 and square it, you come back with a 1. So these are actually the same 3 transformation points that you have over here. There's just, of course, a slightly different shape that takes you through that function. So those 3 transformation points that we had with linear, absolute value, and quadratic functions are going to be really important in the second half of the notes. First thing we want to do is just be able to look at these and identify the function. You're basing it just on the shape. So this one right here is a quadratic function. And we know it's quadratic because it's that U-shaped parabola. Parabola is the official name for it, but it's kind of a U-shaped sort of curve. And then this one is a straight line, but it's not horizontal. So if it's a straight line and it looks like it's diagonal, that's going to be a linear function. If it was a straight horizontal line, that would be a constant function. So you could identify, hopefully, any of these graphs. And now you'll notice that, like, this is still a parabola, but it's different from this original parent graph. That's because it was transformed. So we're going to talk about what it means to be transformed in the second half of the notes. So first way that you can transform a function is to translate it. A translation is also known as a shift. So a shift is like up, down, left, right, something like that. Okay, so shifts. Shifts the graph up or down or left or right. Okay, so you will see one of 2 things. Either you will see the original function, and then after the function, you'll see plus or minus some value k. All right, that's what you have right here. You've got the parent function, and then after you have the parent function, you have minus 4. So this goes up if you have plus k, and then it goes down for minus k. So since this is minus 4, your original parent function would be shifted down 4 units. Okay, so now let's see, say you had a function and then inside the function with the x, you added or subtracted a value. And that's like this one. See the difference is this one's inside the parent function, whereas this one's outside the parent function. So if that's the case, you actually do the opposite of what it looks like it's going to do. And that's super important. So you actually go left if it's a plus h, and you go right if it's a minus h. So very important to note that if it's inside and you're going left and right, it does the opposite of what it looks like it's going to do. So let's practice some of these. So translation, and then we're going to graph the function. So this is an absolute value function. First, we need to identify what the parent function is. So this is absolute value. And then you need to identify what the translation is. Okay, so because it's on the inside of the parent function, it's either left or right. And because it's plus 3, I'm moving it to the left. So I am moving to the left 3 units. Okay, so here's how this works. The official transformation. I have my original 3 points. 1, 2, 3 points like that. So start by writing my original 3 points. So negative 1, 1, 0, 0, and 1, 1. So what I'm going to do is I'm going to translate those 3 points left 3 units. So when I go to the left, it's changing my x value. So I'm going to change all my x values by moving them 3 units to the left. So if I move this 3 units to the left, it lands me at negative 4. I'm not going up and down, so it's not going to change my y value. If I move this to the left, I'm going to be at negative 3, not changing my y value. And if I move this to the left, I will be at negative 2. Okay, so all you have to do to plot the new function is you just plot these new points. So let's do that. So So negative 4, 1, negative 3, 0, and negative 2, 1 is right here. So you connect the dots, turn it into an absolute value graph, and you can see it looks just like the original function, except it got shifted 3 units to the left. Okay, so let's do another one right here. This is a quadratic. See how it has x squared? Anytime you see a squared in there, you know it's a quadratic function. Oops, AD. So it's quadratic, and then you see minus on the outside. So it's separate from the parent function, unlike this one. So down 4 units. Okay, so start with my original 3 points, just like that. So my original 3. And when I move down 4 units, down affects the y value. So that means I'm going to be subtracting 4 from all of my y values. So not changing the x, but I'm moving down 4 units. Not changing the x, moving down 4 units. And not changing the x, moving down 4 units. Okay, so plot those and we'll have our new graph. There we go. There's the second point. And there's the third point. Okay, so now remember this one's a parabola, so it's much more curved than the previous one that we just drew. So this one's kind of a U shape, this one's a V. Pointed, curved. All right, so those are our translations. Next shift or type that we're going to be looking at are reflections. And reflections are what they sound like. They're mirror images, so they're like flipping the graph across an x-axis. So reflections are like flips. Okay, so if you flip over an x-axis, if you see like a negative on the outside of the graph, what that does is it flips over the x-axis. And what it does is it makes the y values negative. So if we're talking about transformations, what it does is it makes the y values negative. And then if you see f of negative x, like if the x is on the inside of the functions, remember it's all about whether the change is happening inside the parent function or outside the parent function. Here, the negative on the outside looks like this. And then here, technically the negative is on the inside. Okay, so if the negative is on the inside, your graph will be flipping over the y-axis. And what that does is it makes all of the x values negative. Okay, so let's do some transformations. So this is an absolute value function. And the negative is on the outside, so we're flipping over the x-axis. So flipping over the x-axis. So let's do our transformation. So our original 3 points are these. So what this does is it makes our y values negative. So nothing happens to x, but our y value becomes negative. Nothing happens to x, and there's no such thing as making 0 negative, so that will actually look the same. And nothing happens to x, and our y value is negative. So plot our 3 new points, and that'll be the graph. So -1, -1 would be right here. 0, 0, still right at the origin. And the third point is 1, -1. So remember, absolute value is a V-shaped, pointed in the center like that. So you can see how it's different from the parent function. It got flipped over that x-axis, which is this one right here. Okay, this is a linear function because it's just a plain old x. There's no absolute values. There's no exponent. So that's just linear. And this you could consider technically the negative to be like on the inside of the function or the outside of the function, because there really isn't an inside or outside of a function with linear. So let's just say that this is going over the Okay, so our original 3 linear points, we have those right here. -1, -1, 0, 0, 1, 1. So start with the originals. And we are flipping over the y-axis, which means our x values become negative. So make this negative and it becomes positive. Nothing changes with y. 0 can't be made negative, so that point's not changing at all. And then here, make this x value negative. Nothing's happening to y. So plot these points. First point is 1, -1. Next point is still 0, 0. And the third point is -1, 1. Okay, connect these. Remember, linear is just a diagonal straight line. So you can see it got flipped over the y-axis. Okay, so that's this axis right here. So it used to be like this, but it flipped over the y-axis. Again, you could see how you could also consider it to be flipping over the x-axis because it was here and then it flipped this way. So either way you want to look at it, linear is kind of a unique situation. All right, last one, dilation. Dilation is a shrink or a compression. Okay, so dilation either shrinks or enlarges, I guess we could say that. So it's either a stretch or a compression. Okay, so you've got a function times f of x like that if you've got a number on the outside. So what you do is you multiply the y values by a. So if that's a 3 on the outside there, you multiply all the y values by 3. And what this does is it stretches the graph if a is positive, like a whole number, and it shrinks the graph if a is a fraction. But either way, you're going to be multiplying all the y values by a. And then if you have f of a times x, like that, if the a is on the inside, you are going to divide the x values by a. Remember that we learned from this right here, that if it's on the inside, it does the opposite of what you think it should be doing. So if you have an a in there, you actually divide the x's by a. Okay, so let's look at our last graph here. This one we have an x squared, so it's quadratic. And we are stretching the y value by 2. So it's on the outside of the function, so that means we stretch the y values, not the x values. So start with your original 3 points. So quadratic starts with these 3 points. And we're going to stretch our y values by 2. So don't change the x's, but multiply the y's by 2. So y gets multiplied by 2. Y gets multiplied by 2, but of course it doesn't matter. And y gets multiplied by 2. So plot these new points, and that will be your graph. Here's -1, 2. Here's 0, 0. And here's 1, 2. So remember, it's quadratic, so it's curvy, not pointy. And if these were plotted on the same graph as the parent function, you would see it's stretched by 2, because our old points were just here and here. So it was wider like that, but it got stretched vertically. Okay, last example. This one is absolute value. Those are pretty easy to spot because you can see the absolute value bars pretty clearly. And then see how the 1/3 is on the inside, not on the outside. So because it's on the inside, you're going to be dividing the x's by that value. Okay, so you're going to compress x values by 1/3. Okay, so start with our original. Absolute value has these 3 as original points. So because of this right here, we are going to be dividing x's by 1/3. So dividing by 1/3, remember dividing fractions is like multiplying by the reciprocal. So dividing by 1/3 is the same as multiplying by 3, which is the reciprocal. So we're going to multiply the x values by 3. Okay, so multiply the x value by 3, y doesn't change. Here, of course, multiplying 0 doesn't do anything. Multiply the x value by 3, y doesn't change. So plot that, and that will be our brand new function. So here's -3, 1, So that point's right there. 0, 0, still the origin. And 1, 2, 3, 1 right there. So this is absolute value, so it is a V-shaped curve like this. Comes to a point at the origin. So you can see this is definitely a compression. Our normal absolute value graph would be like this, so it got compressed. It's like it got squashed, I guess. All right, so that's 2-7.